Good morning, sir.
Good morning.
Good
Good morning.
Oh, good morning, sir.
morning, sir.
Good morning. At the beginning of the lecture, we have 13 students joining. Before I begin, I will share my screen. And we would just revise what I had already told you yesterday. Okay, we started with this topic on thin layer chromatography, which is a type of planar chromatography. Planar because the interaction of the sample components with the stationary phase are happening on a single surface. Okay, it doesn't involve the bulk material as such. It is a surface phenomenon, and therefore it is called as planar chromatography. Okay, the stationary phase is actually applied to a inert material. It could be glass piece, or it could be plastic, or it could be even a metal foil. Just a minute, I'll admit somebody. Okay, and the sample is applied in the form of a maybe a small spot using a capillary tube or a micropipette or even a syringe. Okay, or sometimes it could also be applied as a thin line. Okay, if especially if automatic applicators are used, as in the case of HP TLC, then it is applied in the form of a zone. Okay, then the plate is kept in a trough which contains a solvent system. As I told you earlier, the solvent system actually could be a single solvent, or it could be a mixture of different solvents. And we use a mixture in order to adjust what is called as the polarity of the solvent system. Okay. The sample components are then carried over the surface of the stationary phase by the action of capillary by the capillary action. Okay, and then the sample components get partitioned between the mobile phase and the stationary phase, right? Okay, and then if we are running the standards along with the samples, then it would allow us to compare our sample components, and we get some idea about what could be the sample components, okay, because we are comparing them with the known standards. Okay, then coming to the next point, that is that what are the different phases which are used. And then I told you that the stationary phases are different types of materials which can be used. For example, silica gel, then we can use aluminum oxide, we can use calcium carbonate, we can use modified cellulosic materials, we can use hydroxyapatite or calcium phosphate. Now, why these different stationary phases are used? Because each of these stationary phase has a certain peculiarity, certain characteristics are there. And based on these characteristics, we are able to separate the different components of the sample. Okay. Because these stationary phases can actually interact with the sample components, right? Then we have two types of plates. One is the manually made plate, which we can make ourselves, okay, by just dipping, for example, a glass slide in a slurry of the stationary phase, okay, and then immediately lifting it out so that we get a thin coating on the glass. Okay, we are going to do this in the practical in the laboratory, and I think you will be interested in doing that. Okay, and usually what we do is we add something called as a binder. Okay, for example, calcium oxide, calcium sulfate is a, or gypsum is a binder which is very commonly used, and the purpose of using the binder is that it allows the stationary phase material to stick on to the inert material properly. Okay, and the other important role of the binder is it doesn't allow cracks to be formed in the material or on the surface. Okay, because we want a very uniform surface so that the separation of the sample components will happen very smoothly, right? Then we have something called as the particle size. Okay, particle size of the stationary phase material is very important. And last time I told you that if the particle size is large, then the number of interactions that will happen on the surface will be few. But if the particle size is small, then the number of interactions will be more. And if the number of interactions are more, then obviously we can expect that the separation will be better, the resolution of the separation will be better. Okay. Then if you are using silica as the stationary phase, then I told you that the silanol groups are present on the surface, or the siloxane groups are there, and these groups determine the hydrophilic character. These groups are also essential for the adsorption phenomenon which happens on the surface. Then silica itself can be modified by using different kinds of functional groups. For example, alkyl groups, nitrile, amine, or alcoholic groups can be added on the surface. And when these different functional groups are added, the properties of the silica will change, and these properties will help us to bind to the different sample components. Okay, and that essentially is helpful for the separation of the materials. Then we can have positively charged or negatively charged plates. Okay, all the different types of stationary phase that I have mentioned here, they can be modified in such a way that we can have either positive charges on the surface, or we can have negative charges, or even neutral charges on the surface. And again, the choice of the type of the plate, whether positive plate or negative plate, that choice will obviously depend upon what are the types of different components which are present in your sample mixture. Okay, and when these different groups are present, then we can have a type of TLC, which is called as ion exchange thin layer chromatography, because basically the interactions which are happening on the surface are based upon the charges. I admit 2 students to the class. Okay. And just as an example, I can tell you that DEA cellulose, that is diethyl aminoethyl cellulose, is a type of cellulose which carries a positive charge. Okay, so negatively charged molecules such as even DNA or RNA, they can bind to this kind of cellulose, and therefore we can get good separation of the nucleic acids. Okay, then we go to the next slide. Adsorption chromatography, and I told you here that hydroxyapatite is a material which has a good selectivity for double-stranded DNA. So double-stranded DNA can actually bind to hydroxyapatite as the stationary phase, but single-stranded DNA or RNA cannot bind. And therefore, it is a very useful tool for the separation of double-stranded DNA molecules. Okay, and usually the mobile phases used for this kind of chromatography are hexane, heptane, propanol, butanol, and so on. Okay, moving then to the next slide. I have told you that a liquid can also be used as a stationary phase. So in this case, whatever solid material or particles we are binding to the inert material, these particles themselves do not function as the stationary phase, but the liquid can function as the stationary phase, just as in the case of paper chromatography. Okay. Then this was very important question which I discussed last time, and that is, how do you decide the solvent system, or what are the different solvents which are added up to form the solvent system mixture? Okay, and this decision actually is based upon the polarity of your sample molecules, right? So as I told you, if the sample molecules are polar, then they will dissolve in the polar mobile phase. If the sample molecules are non-polar, then they would dissolve in the non-polar mobile phase. Okay, but then the problem is that if you have polar molecules in your sample, and if you are using a highly polar mobile phase, then the sample will move along with the mobile phase, and it will not be retained on the stationary phase at all. Okay, and if you are using a non-polar solvent system for polar molecules, then the polar molecules will not move at all on the stationary phase. Okay, so there are two things, two extremes, you can say extreme cases. In one extreme case, Either your sample molecule sticks onto the stationary phase in such a way that it does not move on the stationary phase, and in the other extreme you have sample molecules which are moving along with the mobile phase and they do not stop on the stationary phase. So we don't want both the things to happen. Actually what we want is we want the sample components to move on the stationary phase, okay, not with the mobile phase exactly, but there should be a difference in the you can say mobility, okay, and that difference is what is going to be actually important for your separation to happen, okay. So different molecules in the sample mixture should be carried by the mobile phase to different extent, okay. Remember these words, they should be carried to a different extent, or in other words they should be retained on the stationary phase to a different extent, okay. And when I say to a different extent, it means that you are actually going to separate the different components on the stationary phase. Do you get what I'm saying?
Yes, sir.
Are you all able to understand? If there is any question,
Yes, sir.
maybe you can interrupt me and ask me,
Yes, sir.
because this discussion should not be monotonous, isn't it? It should be an interactive lecture. Everybody should understand. Everybody should discuss.
Okay, sir.
Okay. So after that, I go to the next slide, and that is about the sample spotting. How much sample is to be loaded? So for example, if you do not know anything about your sample mixture, then it is always the best thing to take have a 1% sample concentration. Okay, what is 1%? It is weight by volume. So 1% actually means, say, 1 milligram per ml. Is it okay? 1 milligram per ml. Or it could also be 1 microgram per ml. It depends upon your, yeah, it also depends upon the sensitivity of your method. How sensitively your method is going to detect the sample components on the stationary phase. Okay. And then the sample is actually deposited towards one end of the plate, or you can call it as the bottom of the plate, okay, in the form of a spot. The spot is about 1 millimeter, not never 2 millimeter actually, although I have written 1 to 2 millimeter. It should be 1 millimeter or even less than 1 millimeter, okay, because the bigger is the spot, the it would give you a worse, you can say, sample separation. Okay, smaller the spot, the better separation you will achieve, right?
Yes.
Then how is the sample applied? It could either be manual application by using you can say a capillary or a pipette, or it could be a automatic device which is called as an automatic applicator, sample applicator. So using the sample applicator, uh, the very precise quantity of your sample will be placed on the stationary phase or on the plate, TLC plate. Shamim had some problem, I think. So he's joining again. Okay, then we were talking about the development of the TLC plate. So how do we develop a plate? What is the meaning of development? Development is actually running the chromatography. Okay, so what you do is you place your plates in a chamber. The chamber contains the appropriate solvent system. And not only that, but it is also important that the complete chamber should be actually saturated with the solvent vapors. Most of the solvents that we are using are volatile solvents, okay, like alcohol or acetone, okay, propanol, butanol. So these are volatile solvents, and when you cover your sample, your chamber properly, and the vapors will develop, the vapors will saturate the chamber, okay, and only when the chamber is saturated with the vapors, then you put your plate inside, okay. You can again keep it for some time, and then you should allow the actual chromatography to begin. So why this saturation is essential? If the chamber is not saturated, then there is a probability that whatever run will happen, the chromatographic run will not be uniform. Okay, it will not be uniform. you want the solvent level to rise over the stationary phase as a uniform line, isn't it? It should be a perfectly horizontal line, and therefore the plate should be kept vertically upright. Okay, it should not be tilted. If the plate is tilted, then the then the solvent will not rise properly in the form of a horizontal line, but it will be an inclined line. And if the line is inclined, then obviously all the samples which are placed one after the other, the samples will not be carried to the same extent during the run. Is it okay?
Yes.
Yes, sir.
Okay. Now, when the solvent front has reached towards the other end, close to the top end of the plate, then you are supposed to stop the chromatography. Okay. How do you stop the chromatography? Just remove the plate carefully, okay, very carefully, very gently out of the chamber, and then you keep it for drying, okay, or you can just keep it in the open so that all the solvent vapors will evaporate, okay. But before that happens, immediately when you remove the plate, you have to mark the solvent front, okay, because this is in the paper chromatography we have seen that with a pencil we can mark it. So here also, if it is a you can say if it is a ready-made plate, then it is quite possible to mark the plate with a pencil, okay. But if it is a plate that you have made manually, then you cannot mark it with a pencil. In that case, with a blade or with a pointer, with a needle, you can just scrape out a small line to mark the solvent front. Okay, why this is essential? Why solvent front is to be marked?
To calculate the RF value.
Yes, in order to calculate the RF value, you need the one value which is called as the distance traveled by the solvent front. Okay, if you are not marking the solvent front, then you cannot calculate the distance which is run by the solvent front, and therefore your RF value cannot be calculated, right? Okay, then this is the schematic representation of a TLC plate. I think I need not go into this because we have already understood. Just take a look at this figure, the figure number 2, which shows that the sample X has moved a particular distance and the sample Y has also moved a particular distance. And then what you do is you have to calculate from the distance from the start, okay, that is the line where you have put the sample, to the center of the spot, okay. So this is very important, the center of the spot, and that actually means that your sample is the spot which you get is roughly or more roughly it is spherical, okay. If it is not a spherical spot, spherical, that is circular spot. If it is not a circular spot, then obviously your calculation will not be correct, okay. Then I was talking about the silica structure. There are OH groups, okay, the hydroxyl groups, and these hydroxyl groups are essential for the binding of sample components also. Okay, I think I have already told you about this also. The question whether the spots will stick on to the plate or they will move on over the stationary phase along with the solvent. And then I told you that this all depends upon the polarity of the buffer or your mobile phase, and it also depends upon the polarity of the sample components. Okay, ideally the sample spots should not stick on to just one place. I have 10 minutes for this session. So after 10 minutes, I will restart the meeting. Okay. So what I was telling you, that was about the important, you can say, criterion for a good chromatographic run. The sample spot or sample component should not stick at one place. Okay. And they should not move exactly with the solvent front. The movement should be intermediate, okay, between the start of the chromatographic run to the end of the chromatographic run. And how do you achieve this? That is by adjusting the solvent system, okay. How do you adjust the solvent system?
Polarity adjustment.
Yes, polarity. You can add different solvents in such a way that the polarity will be adjusted. The polarity should be adjusted in such a way that all the sample components will be separated from each other properly on the stationary phase. Okay. How do you do that? How do you know that which is the best solvent system? How will you know which is the best solvent system?
Depending on samples, sir.
Depends on sample. Okay. Suppose I give you 2 or 3 amino acids.
Sample.
How will you do it?
What, sir?
Suppose I give you a mixture of amino acids. Okay. How will you select the best solvent system for separating the amino acids? Anybody from Aishwarya? You were absent for a few days. Can you hear me?
Yes, sir. I do hear you. Actually, sir, I called you and I told you that I went for Andaman for a week.
Yeah.
So there was no geo. Yeah, there was no geo network there. So all my activities was going on only on Wi-Fi.
Even after coming back, you were not present. I think for a couple.
Yes, sir. Yesterday only I came.
Okay. It's okay. Okay. So did you get my
Yes, sir.
question? Have you understood my question?
Yeah. Yes, sir. Yes. I told to the Kshamata to record all the lectures, and she sent all the lectures to me, sir.
Okay. I'm talking about the question which I asked just now.
Sorry, I heard that is lecture.
My question.
Please repeat, sir.
Yeah, my question is, how do you select the best solvent system for a particular separation?
Depending upon the solution.
Depending upon the sample.
Solution, solute and solvent reaction.
Yeah. Anyway, so I have not answered this question, and therefore I think I should tell you about the answer. See, there are basically 2 things we can do. Okay, we have 2 options to select the solvent system. One option is like this, that you go for empirical solution. Okay, empirical means what? Something which is already known to people. For example, if I'm trying to separate amino acids, okay, then what are the different solvent systems which other people have already used for amino acid separation? Okay, so I go to the literature, I go through the books, I go through practical manuals, okay, or maybe last year's journal we can refer to, and then whatever solvent system the earlier people have used, that same solvent system I will use for my separation. Is it okay? That is called empirical selection, right? And the other method is trial and error method. So what is trial and error method? I will use a couple of different solvents, okay, solvent systems, okay, whichever solvent system gives me the best result, that solvent system I will use, okay, or I can increase or decrease the polarity. For example, if I use ethyl acetate, okay, then ethyl ether, okay, ethyl ether is a polar solvent. Okay, so if I go on increasing the amount of ethyl ether in my solvent system, then that will make the solvent system more and more polar. Okay, so initially maybe I'll start with 0 amount of ethyl ether in one solvent system. If I don't get good results, then I will add some ethyl ether. If I get slightly better results, but I want even more better results, then I will increase the amount of ethyl ether until the time when I get very good separation of the sample components. Is it okay? Even water is a polar solvent. So I can increase or decrease the amount of water. I can increase or decrease the amount of, say, hexane. Hexane is a non-polar solvent. Okay. So by altering the relative concentrations or relative amounts of the different solvent systems, I should be able to get, I should be able to come across a certain solvent system which will give me the best results. Do you follow me, everybody?
Yes,
Yes,
sir.
sir.
Yes,
Yes.
sir. Yes, sir.
Yes.
See, now here I have given you a list of different solvents. Alkanes are the least polar, okay? And then starting from alkanes, we go to increasingly polar, okay? Increasingly polar solvents, for example, alkyl halides, Then there are alkenes, then there are aromatic hydrocarbons, ethers, esters, ketones, aldehydes, amines, alcohols, and the carboxylic acids. Carboxylic acid are the most polar solvents. Okay, so I can mix, I can make a mixture of some of these solvents to get the solvent system. Okay, and by trial and error, I can come to the best solvent system, which will give me a good separation. Right. So this is an example again, if we want to separate lipids, for example, okay. The lipids may be extracted from plant leaves, they can be extracted from seeds or animal tissues. We can also extract the lipids from bacteria, okay. And then we can use solvent systems like ether, acetone, hexane, or we can have a mixture of chloroform and methanol in the proportion of 2:1. We can have a mixture of hexane and isopropanol in the ratio of 3:2, and so on. So these are empirical solvents which are already used for lipids. Okay, we can try out one of them, okay, or all of them, and whichever gives the best result, that solvent system we can use for lipid separation. Is it okay?
Okay, sir.
So this is again an example of separation of lipid. I will skip this slide. Okay. Just as an example, I have given here solvent system hexane, diethyl ether, and acetic acid in the proportion of 80:20:1. Right. So this solvent system can be used for separation of lipids like we have, for example, glycerophosphatides, sphingolipids, or glycolipids, or glycerols, different kinds of glycerols. Okay, and they can be separated using this solvent system, right? And then how about identification of the spots? We can keep the plate, TLC plate, in a chamber which contains iodine crystals. Okay, so iodine vapors will be formed, and these iodine vapors normally they react with all kinds of biomolecules and give them a dark brown color, okay, or reddish brown color. Then again, this is about the detection. We can use fluorescent detectors. Okay. For example, if we add a zinc salt in the silica gel before preparation of the silica of the TLC plates, okay, then the zinc salt will render a fluorescent background, and all the sample component will appear as dark colored spots on a fluorescent background. We can also use concentrated H2SO4. Okay, this is a very, you can say, universal kind of a detector. Okay, so H2SO4 will be able to detect all the organic substances in the form of black colored spots. Okay. Then if you want more specific kind of detection, then ninhydrine solution can be used for detection of amino acids. I think you might have heard about this, or you might have performed paper chromatography of amino acids in your BSc. Have you done it?
Yes, sir. Yes. Yes.
Yes, sir. Yes.
Then coming to the measurement, I have already told you in paper chromatography that we calculate the RF values. Okay, I'll go to the next slide. This is very important slide. There are two different cases which are shown here. See, the two spots are appearing here, which are separated from each other. And there are two spots here which are not exactly separated.